Your team has been sprinting for weeks. You've written the logic, compiled the code, and hit deploy on an AI-assisted code review tool. According to the spec, the tool needs to perform a few specific actions. A developer submits their code, the system generates LLM-based review suggestions, and the user marks those findings as resolved. In your staging environment, it runs flawlessly. The buttons click, the data saves, and the exact workflows you designed execute perfectly. From a purely behavioral standpoint, the code meets every requirement. But that progress creates a false sense of security right before the real users arrive. Launch day hits. The feature goes live to the entire company, and that isolated test environment is instantly replaced by a flood of unpredictable traffic. First, the interface freezes. The normal internal usage volume overwhelms the system, and the dashboard simply stops loading. While users are stuck waiting, a deeper flaw emerges. An unauthorized user manages to view an application not assigned to them, exposing sensitive source code. Then the LLM hallucinates, crashes the background job, and breaks the entire review workflow. Your software has all the right features, but it's slow, insecure, confusing, and unreliable. Behavior without constraints is ultimately a disaster. To understand why this happens, we have to look at how we define requirements. Functional requirements explain exactly what the system should do. Non-functional requirements describe how well the system should behave under pressure. Take a look at this structural model. The visible top portion represents functional behavior, the buttons, the inputs, the explicit actions a user takes. But that visible layer rests on a massive foundation of non-functional quality, things like performance, security, and scalability. If you build the top without reinforcing the bottom, the entire structure collapses the moment real weight is applied. Functional requirements define a feature's existence. Non-functional requirements dictate its survival. Let's rewind that failed launch and patch the code using specific non-functional pillars. To fix the dashboard freeze, we apply strict performance and scalability constraints. The UI must now load within an acceptable time for the expected data volume, and the review service must progressively handle larger repositories as they grow. Next, we stop the data leak. Under security, we mandate that API endpoints validate permissions, so users only see their assigned apps. Under usability, we add clear error validation, so users aren't left staring at empty states. For the LLM crashes, we establish AI reliability rules. The AI must return structured output, and any generated recommendations must be clearly marked as suggestions, not absolute truths. Finally, we set general reliability standards. If an API call fails, the background job must automatically retry without losing important data silently. By enforcing these specific constraints, the user experience shifts from chaotic and fragile to stable, fast, and entirely under your control. But the users are only half the equation. You also have to consider the engineers who will inevitably have to update this code 6 months from now. This is where maintainability comes in. We separate the API code from the database access logic and use clear, consistent naming conventions so the next developer isn't left guessing how the structure works. And when things do break, we rely on observability. We configure the system to log important errors and include traceable context for AI workflow failures, giving us a clear path to debug the issue. High-quality software accounts for 2 separate life cycles: the user experiencing the product today and the engineering team tasked with updating it tomorrow. Achieving this level of stability requires precision. You cannot write a vague requirement that says the system should be fast. You have to write a testable constraint, like search should return results quickly for normal internal usage. This layout for an AI code review tool separates specific developer actions from the quality constraints at the bottom. By grouping these requirements into 2 distinct lists, the specification defines exactly what should happen and how the system must hold up during the process. Adopting this 2-section structure for all documentation ensures that every intended action is paired with a specific expectation for quality. Explicitly writing down these constraints provides a concrete checklist for testing, ensuring that reliability is an engineered target rather than an afterthought. Avoid the common trap of treating performance or security as later concerns. And do not assume that autonomous agents will automatically handle quality guardrails on your behalf. When you launch your AI code review tool with these pillars in place, it weathers the storm. The traffic spikes, the models process thousands of requests, and the system holds steady without dropping a single workflow. Writing functional requirements makes you a programmer. Defining the non-functional requirements makes you an engineer, capable of building software that actually survives the real world.